Fine, so my name is Ivan Arakistain. I work as a researcher for Tecnalia. Tecnalia is the biggest research institute in Spain, the biggest private institute, and we are like 1,500 researchers. Our team works with edge computing. So in this seminar, I'm talking about the use of TinyML embedded AI systems for predictive maintenance. This is what I said about Tecnalia, the largest applied research technological center in Spain. This is our team. We focus on embedded systems and small artificial intelligence models. Okay, so let's start. We focus on urban infrastructure. It can be different things like elevators, bridges, railways, windmills, different sort of infrastructure. And in many cases, our work is related to vibration monitoring, but not only. We can use other use cases also. Edge computing is very important in this regard because we need to minimize the transmission of data. So we try to make computing in the device so we can make decisions and only transmit which it is required. And we want to detect in an early way if there is any sort of damage in the bridge, in the railway, or whatever. So I will discuss some applications we have been going through. The first one is a digital twin of public elevators we did in our hometown. And in this case, we designed a PCB, which is to be embedded into the cabin of the elevator. You can see we did it in 3 elevators, and we installed the device. So we've got a STM32 microcontroller and different sensors. The most important ones are atmospheric pressure to know the height of the elevator, accelerometer, if it's moving or not, presence on occupation sensor to know if there is someone inside, and last we used also a microphone. So we did some testing, and okay, the goal is to make a sort of a digital twin, a small digital twin, and to know if everything is working fine in the elevator or it's under maintenance, it's stopped, if it's available or not. Okay, we did a dashboard, and yeah, this is a small demo, but yeah, I wanted to notice that in accessibility.cloud, it's a German initiative, and they have like 3,000 elevators monitored. This is very important, mainly for people who have difficulties for mobility, so they can know beforehand, before they do the journey, they can know if the elevators, the escalators, everything is working, and they can do the route, or they have to make some changes. So this is quite a social or good initiative for the area. And in this case, we also used a microphone, and we used TinyML to classify different sorts of sound. In this sense, for a microcontroller, it's quite a difficult task to classify sound because it's a complex signal, as you can see. So we convert the sound signal into a MEL spectrogram. The MEL scale is a mathematical transformation, and you convert the complex wave in sort of an image. So for the microcontroller, it's much easier to understand the differences between images than between complex waves. So this way, we can classify between different sound. We used a data set, which is Urban Sound 8K, and we've got lots of sounds in 10 classes that we can train our model. Okay, this is one application of TinyML. Another application we are working on is structural monitoring for bridges. In this case, we try to monitor if the natural vibration frequency of the bridge is correct, or if there is some sort of change in frequency or amplitude that could indicate that some structural damage. So we installed MEMS accelerometers, which are quite cheap and accessible. We are able to sample at 6 kilohertz. And as you can see, MEMS accelerometers are quite cheap from ST also. And in this case, we wanted to double check this cheap accelerometer with a laboratory accelerometer, which is much more expensive, but it's like the reference one. So we did the transformation, the effective transformation, and yeah, we've got quite good results, both with the laboratory accelerometer and with our cheaper one. So we are quite happy with the results, so that we can know if there is going something wrong with the bridge. Last but not the least, we are also working with the operational anomaly detection with windmills for energy generation. And in this case, what we try to detect is anomalous vibrations. We measure different normal vibration patterns, and we build a data set that we have to tag and to be able to deploy a model of TinyML. So in this case, we've got normal accelerometer readings and abnormal ones. So with, for example, 50 samples or something like that, we can create a small model. And here I have a small video. We also did so.
Through this platform, the eolic parks and its wind turbines operation data can be visualized in several dashboards which are geolocated over 2D and 3D maps. The platform offers the possibility of monitoring in real time the different operating variables of the wind turbines, being able to act remotely, if necessary. In addition, it offers the possibility of managing the life cycle of the entire infrastructure by integrating the performance of inspection and maintenance tasks with drones. The videos generated by the drones are processed and streaming within the platform, being able to detect the different structural defects through the applicability of artificial vision algorithms. Additionally, it offers the possibility to evaluate and estimate the possible repair scenarios in cost and schedule terms. Finally, this platform provides a structural and operational sanity check environment for the whole infrastructure.
Okay, so our vision with regarding to embedded IA is to be able to have different devices deployed and to be able to modify or upgrade the model over the air remotely. So we are working towards that, and we find that infrastructure an application that requires lots of this kind of sensors. And also we are noticing that particularly due to climate change, many of this infrastructure are under risk of landslide or different phenomena that is happening more commonly. So we've got quite a bit of work to do. So thank you.
Hi everyone, my name is Anshuman Fauzdar, and today I will present the topic Predictive Maintenance in Industry 4.0. So today I will covering the team introduction, the project inspiration where it started, the overview of project, the impact on local community it had, and what is the next stage of the project that we are working on. So, who are Team Mechatronics? The humble beginning. Me, Anshuman Fauzdar, my two friends, Akshay Goyal and Sunny Vedwal. We were college friends who worked on very small projects and ideas. But we joined full-time jobs after our college, and we left it after few months after getting an opportunity from IIT Madras to join as entrepreneur in residence. So how did we land it here? We found hackathon named Samvedan 2021 that was organized by IIT Madras and Sony, in which we got the first prize for the problem statement of predictive maintenance that's using the Sony's Presence microcontroller. So where is the project inspiration that we started on? Initial inspiration came from my father, who is part of manufacturing industries for last 25 years and have major experience as quality head in various domains. And we discussed problems, how things are happening in industries in general, and it caught my attention. Even he showed me various videos and incidents that happen on the shop floor, what is specially done on the quality side, and implemented different pokayokes to ensure that such things should not happen, but still things happen. So when I initially started working on the problem statement in college time, I chose automated surface visual inspection, but it took a turn. After applying in hackathon, I got hands-on experience working on problem statement of predictive maintenance. That's in Industry 4.0 domain, and that we used Sony's Presence and Edge Impulse as a platform for the TinyML part. So what is this project all about? What is the overview of the project? Predictive maintenance contains many subsystems that need to be interlinked to make the ultimate solution work. You need each and every point to be working to make application work on the last. So we kept pain points and problems that are faced in day-to-day life of the manufacturing activities of a manufacturing company owners and the operators who are actually working on the shop floor as the top priority when developing the prototype. So we identified some problems when we started. First one was the labor problem. The workers leave without any notice. It's very difficult to train new one. And there is an operational cost that is associated with the machines and the operators. The energy bill has increased after the wear and tear or the improper maintenance of the machinery. There is efficiency and productivity loss also. And they do not have any idea of what utilization their machines are running on. And they only rely on experienced workers to set machine parameters to make it right. And the biggest one is the operations. The frequent breakdowns cause big losses. These can be direct and indirect losses on the business and the application of the industry itself. And the data and the records, guess what? They are still in the 90s. They all noted down in by paper and pen. So ECMA also identifies all these points in the manufacturing. ECMA is the automotive conclave for the manufacturing. So when we started, we made very bold decision while designing our prototype. Despite of the technological development, majority of manufacturing industries have old red machines which need retrofitting. And we thought retrofitting is the right option to utilize data points from the machine. So we started designing the module in such a way that modularity is in core design. And yes, we needed the expansion methods to connect to various sensors and sensor fusion and ensure long-term technology availability to the machine and the whole facility of the manufacturing itself. Like in the photos, you can see there are CNC turning machines, lathe machines, MNTR. They are all old, but our module can work on each and every one of them. So in prototyping stage, we made three major components. First one was the sensor and camera node module. So what is this? It's a sensor fusion and image processing combined as a stackable solution. Like you can keep one sensor module and keep a camera module and combine in such a way that you get multiple data points coming in. Second one is the gateway. To gather decision from the node device that is running HML, we have to provide a human readable data that can be also doubled as HMI, in which the associates can put in their data. Associates or the worker that we are referring to again and again. Third one is the software platform. HML capability is the main selling point of this prototype that need to be run on the node module. And it provides dashboard, notifications, API connections, ERP integrations, all within a single ecosystem with modular connectivity options. All big thanks to Sony's Presence and the Edge Impulse at that time that allowed us to make such a prototype in a very small time. So it came part of the deployment. Major part of the project was focused on deploying in such a deployment infrastructure that solves real-world problem to predict potential breakdown, maintain safety, and optimize efficiency of the machine. For prototyping stage, we used a 3D printer to mock up the situation, and we tested several sensor fusions, and we got accurate results showcasing the capabilities of our prototype. So let's see in the next slide, demo. First one is the image classification that we did. To detect any unwanted human interaction with the machine, it gives notification in real time. And any unwanted hindrance, any object that comes between the printer, it notifies in real time and can be extended to fast decisions that can be taken in real time. Second is the object detection. What if your machine is producing wrong material and you are not there to overview it? You got it. It will track the overall deployment of the machine, how much it is running, is it on the right track, is it producing the right thing, and on a certain threshold, it will alert you that something is wrong with the machine, fix it ASAP, and you get a very fast decision, and that leaves you a very precious time and money. And third one is the unwanted noise or disturbances that can be caused due to faulty fan, motors, or even any other situation that might as a hindrance to your machine. And fourth one is the sensor data. Now we also infused several various sensor points that I told, and these sensors include the temperature, pressure, altitude, and GNSS that we are able to track the machine in real time and the parameters that are very crucial to the machine. So how did it impacted the local community? We won the hackathon and our college supported a lot. After winning the hackathon, we interacted with our college juniors. So they are working in a very diversified field like sustainable food consumption. And they are also saving wildlife and very interesting similar topics. And I was part of Microsoft Learn student ambassador community. So I got the opportunity to share my thoughts and the process that was involved by making the prototype and all the technological development with my peers and even the Microsoft team. And after the hackathon was over, we interacted with many owners and operators of the manufacturing industries. And we told them that predictive maintenance is a very cost-effective technology, which is not only about the predicting of an anomaly or the condition of the machine, but also make their plant Industry 4.0 ready with several additions like counting Pokayoke, maintenance authorization, digitalized Kanban, and so on. So what are we working on now? As I told you, we have left our full-time job and we are now entrepreneur in residence. So now we are closely working with a traditional machine pharmaceutical company who are using traditional machine to manufacture Ayurvedic medicines. In first phase, we are providing digitization of steam boiler. So we have successfully demonstrated the capabilities of asset management, real-time data streaming, and the integration of predictive maintenance within their ecosystem. So as you can see, this is the HMI that we are offering that takes automated data from the boiler. And this is the sensor module that we have developed, and it is taking data in real time and making decision on the edge itself. So if you can see in this video, we are installing the sensor module. And the sensor module design is made in such a way that it is very modular and you can mount it in any size, any way, any shape. And the HMI offers a very easy access to the associates by entering the points that they were earlier writing down on a pen and paper, and this was not transparent to their management. And management is quite happy with the results. They are now able to see into the data points of their boiler and they can make fast decisions. And we are also committing them the carbon neutrality to showcase the smart city consumption because they are in the middle of a city and they do not want carbon to be increased in any way. So next up, we are planning to register ourselves as company and incubate and raise seed round. And we are also working on scaling up the solution which we have made, that are the sensor module, camera module, the HMI, which also doubles as a gateway, the software platform. And this is made by utilizing the technology and the hardware which has so far been developed. And we are planning 3 case studies. First one is the computer numerical control, that is the CNC that are used in manufacturing industry. Second one is the heat ventilation and air conditioning, HVAC, in the both professional and personal home devices. And third one is a very interesting one that is in the medicine field, that is autonomous digital stethoscope on a very large scale. And last, very big thanks to Hackster for providing this opportunity and all the support that helped me and my team to shape this talk and share my journey and thoughts. And there are amazing people who are working on open source software and hardware, which helped this solution to build so much quickly that even in months we were able to build such awesome solution. So thank you. That was my part of the predictive maintenance, and all the best. And these are my socials. I am Anshuman Fauzdar at every social media. Do connect with me and share your thoughts. Thank you.
Hello everyone, this is Pradeep. So in this session, I'm going to talk about my project, which is predictive maintenance with Blues Node Card and VO Terminal. So first of all, let me introduce myself a bit. So I actually introduced my name, right? It is Pradeep. So I'm actually living in India and currently working as a VLSI chip testing engineer. Apart from my work, I'm doing blogs on IoT, embedded system, and machine learning in all the online platforms like Hackster and some other platforms. Apart from this, I'm also part of the ambassador in Blues and Qubitro. So that's all about myself. Maybe we can move on the next one. So in this presentation, I'm going to showcase my project, which I have done. So these are the agenda which I want to follow. So the first one is the motivation. So what is the main motivation for this project? The next one is what I have done in this project. And the third thing is ingredients, what I have used for this project, then the project flow, and some of the future development about this project. So first, let's start with motivation. So as we all know, right, in this year 2023, we have more advanced technologies in all the industries like medical, automobile, everything. In all the industries, we have more advanced technologies. So in those additional to this thing, we have that industry 4.0, which increased the automobile industry productivity over more than 200%. So when we're increasing the productivity, we need to monitor those machines and industrial motors continuously 24/7 and 365. So we need to monitor all these things in every day and every time. So what we can do now, we can use machine learnings to monitor those machines. And if there's any anomaly detected, we can make an alert based on the machine learning. So we can use machine learning to detect whether the machines are good or bad. Then the next thing is, once we find out whether the machines are good or bad, we need to alert the users whether we need to stop the production or whether we need to continue the production or whether we need to alert the user. For the thing, what we can do now, we can use IoT to do those alerting and SMS and everything what we can do. So this is what I have done for this thing. So to address this issue, I have created a system. What that can do now, that can monitor the motor vibration using the vibration sensor continuously, and using the machine learning, if there is any abnormal activity on the motor is detected, it will just alert the user via SMS or email. So by using this system, what we can do now, we can decrease the downtime and we can increase the maintenance. So we can increase everything on this automobile industry and we can increase the motor health. So, so this is the ingredients which I have used for this project. So when coming to the hardware side, I have used the Blues node card, which is a cellular-based node card, to transmit our sensor readings to the cloud. And the next one is node carrier. So the node card is just this green thing. So we need to connect this node card to our hardware. For that, we have just separate node carrier. Okay, so by using this node carrier only, we can connect this node card to the controller. Then the main part of this project is this VO terminal, the Seed Studio's VO terminal. So this is the hardware which can actually detect the motor data. Then based on the data, it will find out whether there are any anomalies or not. If there is any anomaly detected, it will just send the alert to this user using this node card. So when coming to the software side, we are having Arduino IDE, so which is the global thing to program these controllers. Then the Blues node card. This Blues node card will transmit all the data to the node hub only. So once we got the data to cloud, we need to visualize the data. To visualize the data, we are having this Qubitro platform. So by using Qubitro only, we are going to do the visualization. Then we are going to use edge impulse to detect the motor anomaly. Okay, so this is the workflow which I have followed. So we can just look at this image. So first one is we need to collect all the sensor readings from the VO terminal. Then we can use edge impulse to detect the anomaly. Then if there is any anomaly detected, we can send those data via cloud via this Blues node card. Then we can use Qubitro to visualize the data. Then using webhooks, we can trigger alert or we can trigger the alert to the user. So this is the 5 steps which I have followed. So let me show you one by one. So the first thing is we need to collect the motor acceleration data via this VO terminal. So you can see this is the VO terminal, it's just a block overview. So you can see it is just a simple on microcontroller which contains I2C ports and other group ports. And it also contains inbuilt accelerometer and gyro sensor, and it contains light sensor, IR emitter, and some other sensor. So in this, I'm going to use this accelerometer to measure the motor anomaly. And if there is any anomaly detected, it will just trigger the alert to the user. So in order to find the anomaly detection, we are going to use edge impulse. So we can use edge impulse directly on the VO terminal, or apart from this, we can use this platform called CodeCraft. So we can use CodeCraft to do the anomaly detection. We can create anomaly detection model using this motion recognition system. Then we can find out whether there is anomaly or not in the motors. So in the third step is once we find out, once we are able to detect the anomaly, we need to combine the VO terminal with our node card. For this thing, you can just look at this code snippet. So you can see if max confidence label is vague, if there is any anomaly detected, it will trigger the alert initiator message via the Blues node card. So this is how the serial terminal look like. So you can see it is ideal. Ideal is 0.6%. The wave is 0.3. So there's no anomaly. In this part, you can see the ideal is 0.3. The wave is 0.6, which is anomaly detected, and it is going to trigger the alert to the user. So the next one is once we find out the anomaly, we need to send our sensor data to cloud. So for that thing, we are going to use Blues node hub. So this is how the data look like in the Blues node hub. You can see the anomaly score is 100 and the status is anomaly detected. So this is the previous one. Anomaly score is 0 and the status is no anomaly detected. So once we got all our data in the cloud, we need to visualize. So this is just a raw text format, right? We need to visualize those data. To visualize these data, I'm going to use Qubitro as a MQTT platform. So this is just a dashboard when we are creating a new project on Qubitro. So you can see our public address and username and password. Then I'm going to use those credentials in the Blues Node Hub root page. So in the Blues Node Hub, I'm going to create a new root. In this root, I'm going to put all my Qubitro credentials to transfer my data from Blues Node Hub to Qubitro. So once I transfer my data to Qubitro, I can actually visualize my data in Qubitro platform. You can see all the anomaly scores, my status, all the data is appeared here, which means I'm going to transfer all my Blues Node Hub data to Qubitro via this root engine. So once I can able to see my data, means what I can do now, I can create a new dashboard. So this is my dashboard, you can see. So it's showing location and it is showing the anomaly status and it is showing the anomaly score. So in each interval, how a anomalies look like. So once I got my visualization, what I can do, I can make a alert system. So Qubitro has inbuilt webhooks and Twilio triggers actions. So you can just use webhooks to trigger conditions. For example, if my anomaly score is equal to 100, it will trigger the alert message to the user. So this is how the webhook algorithm look like. So you can see when my anomaly score is equal to 100, it will trigger the webhook message. So you can see it will just trigger the webhook and you can see all those data in the webhook page. So this is how the system look like. Maybe I can just show you the demo. Okay, maybe you guys can able to see the VO terminal, which is connected to Blues Node via the simple groove cable. Okay. So for now, I'm going to first delete this. Okay, it's triggering the message. Okay, so I hope you guys are seeing my screen. Okay, so you can see whenever the alert is detected, okay, you can see the red and blue message. Whenever it detected, you can see in the webhooks, it's just triggering these webhook messages. So you can see it is anomaly detected, the score is 100, again, and again. So whenever the anomaly detected, it will just trigger the alert message to the user. And also you can visualize all your data in the dashboard. So this is how my dashboard look like. So it's showing the location of my node card and the anomaly status and the anomaly score. So this is my this is my Qubitro page. So you can see the status of the incoming data. And this is my Blues node card page. Let me refresh this again. Okay, you can see all those data. So anomaly score is 100, the anomaly detected or not, it will show everything. Okay, so now we know how this system is working and what is those process about. So next thing is the future developments. So in future, what we can do now, we can actually use additional sensors like, so as I mentioned, right, this VO terminal has some more sensors. So we can use those sensors to detect some other anomaly status, and we can improve the machine learning algorithm to detect most of the kind of all the detect failures. And we can create our own mobile app to receive the notification and control the systems via remote. So that's all about my project. So thank you guys. Thanks for joining. And if you want to know more about this project, please visit this QR. You can know about my project. And if you want to ask any question, just scan this QR to connect with me on Twitter, and you can just ask questions, whatever you want. Thank you guys. Thanks for joining.
Hello, my name is Pablo Zuloaga, and I'm the founder of PowerSTEM. We are a research and design studio of educational technology based in Barcelona. And today I'm going to talk to you about POWER, the Plant Observatory of Weather Adaptability for Resilience. According to a study of ETH Zurich, it is predicted that by 2050, London is supposed to have a weather similar than the one in Barcelona. And Madrid is supposed to have a weather similar than the one in Marrakesh. We have seen that in the last years, temperature has increased drastically. And by 2050, the Earth temperature could rise up to 3.4 Celsius degrees, generating extreme weathers throughout the planet. There it's been said that we have just lived the warmest summer ever, but I think that what we just lived, it's the last colder summer that we're going to have. According to FAO, by 2050, we will need to produce 70% more food to feed the 9 billion people expected global population. Right now, we are 8 billion people living in this world. And even though we are producing enough food to feed the entire global population, there's around 1.2 billion people living in undernourishment and hunger situations. Extreme weathers caused by climate change will increase the droughts and the floods, and these will have a profound effect in agriculture and food security around the world. And even though hydroponic gardening in urban areas might seem like a solution towards food security and food sovereignty, we should never forget about these people, the smallholder farmers, because 2/3 of the world's poorest population works in something related to agriculture. This means that the people who brings the food to our tables are among the poorest people in the world. And this situation doesn't seem that it's going to change. It seems that it's going to get worse for them because of climate change. Most of all, because of the lack of access to proper data that could allow them to take informed decisions toward climate resilient agriculture. There is no data probably related to certain crops or focused on their specific regions. Most of the data is generated for industrial agriculture or for industrialized big farming processes, not for smallholder farmers. That made us ask ourselves, how might we anticipate the effects of climate change to move into a future-proof farming practices? And since in POWER, we are a research studio focused on education tools, And we believe that empowering kids, it's a way towards a change, to turn them into future change makers for the world. We also asked ourselves, how might we teach the effects of climate change in a more practical way to these kids? That's why we created POWER, the Plant Observatory of Weather Adaptability for Residents. POWER, it's a low-cost, open-source climate simulator to grow food under future predicted weather. It's a box with some sensors and actuators inside that connects to a web platform. In this web platform or interface, the user can select the weather of a specific city they want to simulate inside of the box. The platform does a web scraping process where it gets the information from a weather API of the selected weather of a certain location, and it does some algorithmic conversion to simulate this weather inside of the box. Like, for example, considering the sunrise and the sunset time, and then it kind of simulates the percentage of light that would be in a certain moment of the day. It also tries to replicate the temperature according to what the sensor, what is happening with the sensors inside of the box. Also the humidity and the rain and so on. POWER has sensors inside like temperature, relative humidity, soil moisture, pH, also CO2, which, sorry, it's not on the list. It has actuators like grow lights, irrigation systems, heating systems, and cooling systems. And the main brain of POWER, it's a WIO terminal, a microcontroller with an integrated LCD screen with Wi-Fi, Bluetooth, and LoRa capabilities, and multiple GPIO pins. We designed also an IoT board to connect the WIO terminal to the sensors, actuators inside of POWER that can handle 24 volts, 12 volts, and 5 volts, and extend or expand the WIO to multiple analog, digital, and I2C GPIO groove connectors. This board, it's open source, and actually the documentation, it's uploaded in Hackster.io if you want to look for it, also the POWER documentation. And what it does, it's that it also controls relays that control the water, the sunlight intensity, the temperature, and the irrigation based on the selected weather. POWER started in 2019 as a dream. It was called the Plant Data Gathering Machine, and a speculative design, a box with an connected to an Arduino. Then we started drawing some sketches, some Illustrator designs, some 3D renders, and also some speculative renders of how it might look in the future. Then we arrived to our first prototype in 2020. By the summer, it was the middle of the pandemic, and we improved that prototype in 2021 when I was doing Fab Academy at Fab Lab Barcelona. And this is the actual version, a version that actually came from a contest in Hackster.io, also sponsored by Seed Studio, where they were testing this WIO terminal, and we integrated it to POWER. And in that iteration, we discovered the power that the WIO terminal could give, or all the capabilities that it could give to our device. These are more pictures of the latest prototype, the prototype controlled by a computer. And this is part of where our dreams start happening. Kids using POWER, experimenting with POWER, learning and playing with different plants around the world. Because we envision a future in which different kids in different places could experiment with a lot of different plants at their school, at home, learning the effects of climate change in the plants, learning about food security and food sovereignty. Right now, we are working in collaboration with RMIT University in Melbourne, Australia, to design a web platform to control all of these POWER devices that could allow the teacher or the user to integrate different POWER devices or to connect them, to generate projects research projects based on different kinds of plants and different weather conditions. They could also select the weather conditions according to different cities around the world or any city around the world, or also set some manual controls in case they want to have some specific heating, cooling, irrigation system or lighting system, or make some presets. But the most important of all is that we are adding the capability of generating a database where students around the world could save all of their experiments. Because, as I was saying, we envision a future of a lot of power devices in a lot of schools, generating data and experiments, a distributed network of data, of interconnected schools exchanging data about their experiments with different plants under different future predicted weather conditions. And between all of them, we could create an open knowledge database that can feed predictive AI models that can help smallholder farmers to make more informed decisions and thus become more resilient to climate change. Urban and rural communities connected in a distributed network. Because even though we might not be able to change the climate nowadays, we can predict it and therefore anticipate to it. Thank you very much. I'm Pablo Zuloaga, and we are PowerSTEM. And our purpose is to empower people with knowledge, technology, and data for a planet-centered future. Thank you.
Hey everyone, thanks for joining in for my talk, and also of course thank you Hackster for having me on the Impact Summit. My name is Samuel Alexander and I'm a hardware maker and designer from Indonesia. So before diving into my project, the AI plus IoT recycle bin, I'd like to give you some context on the issue of recycling and also its impact on the environment. It's predicted that about 50% of all waste could be recycled, but in reality, only 10% can be successfully carried out. The rest cannot be carried out because the materials were not sorted properly. And improper waste disposal, which means the mixing of different materials in the same bin compartment, makes it challenging to recycle effectively. If the different materials got mixed or contaminated, it will have to be resorted before the recycling process can begin, and this is something very hard to do. So that's why most of the materials just end up in the landfill. And so by now it should be clear that to increase in the recycling efficiency, the materials should be sorted right at the bin itself, so the recycling materials can be properly processed to reduce the burden on landfills and of course leading to smarter and more sustainable cities. This is the video of my AI recycle bin. Just keep in mind that this video is sped up so it doesn't take too long to watch. Yeah, and for creating this project, the initial thing to do is first collecting the data of different sounds or different sound from the materials that we're gonna collect in the recycle bin. So I've selected plastic bottles, cans, paper, and also for the last item is others. But in this in this project, I wanna use ping pong balls just to demonstrate that we can select different kind of materials depending on the use cases. And for this, I just selected ping pong balls. So for collecting the data, I've set up the same rig that would later be used for the recycle bin prototype. But at this stage, I haven't placed the actuator. So for my initial test, I collected the data using the Arduino Nano BLE Sense. Then I tried adding more data using my phone's microphone, which also works. So for building the AI model, I used Edge Impulse, and I'm sure like many of you here are already quite familiar with the processes, but in case you're not, the initial step after collecting the data, then I'm creating the digital signal processing feature extraction. The default numbers here, the default parameters should work, but I changed the low frequency cutoff so that the wind noises and humming noises can get filtered out. And from this, as you can see, we get a 90.6% accuracy. This proves that the idea actually works, that we can sort different materials based on their sound. But for my case, there is still room for improvements by changing the parameters, adding more data perhaps. And this is one of my initial tests, which when I get this 90.6%. After we have built the model, we can deploy it on the edge, which means putting the firmware into the microcontroller boards. I've tested this project using the Arduino BLE Sense and also the Seed Studio Xiao BLE Sense, and also more recently I tried using the Nikla Voice. And with the latest version of my project, because I've separated the actuator control and the inferencing board, which those two communicate via I2C, this means we can test different inferencing microcontroller boards without rewiring and rewriting the actual control, the actuator control software. And yeah, for the controller board carrier, I also designed it using the Arduino MKR style pinout, so we can change different microcontroller dev boards depending on our connectivity needs. For this example, I used the Arduino Portenta C33 because I'm using Wi-Fi for IoT connectivity, but we can change this to, let's say, the Arduino MKR WAN if we want LoRaWAN connectivity. For CAD, for the PCB design, I used KiCad, and for the 3D model, I used Fusion 360, and these are a screen recording of you know the CAD models itself. To make this project even more useful in the context of smart cities, IoT functionality is added to the project so we can remotely monitor multiple recycle bins that are deployed in the multiple locations. By being able to monitor, it means we know when the bin is full and the materials can start being collected. But the IoT integration phase of this project is still under early experimental stage and still need research and testing. So this is one of my initial testing. This video, when I record this video, I haven't turned on the actuators, I mean the servo motors and the stepper motors. So this is just to test if the IoT cloud works, and it does work. Yeah, so you see it does work and can be integrated into the project once we turn on both the actuators and integrate the IoT. Then yeah, the concept is finished. We have integrated AI and IoT into the recycle bin, which I hope can be deployed in places like this. This is Taman Surabaya, one of the public parks in the city where I live. I hope that the AI and IoT recycle bin can be deployed to, public areas like this and can offer a potential solution to improper waste disposal by utilizing AI and audio recognition technology. So it promises to improve recycling rates, reduce landfill usage, and hopefully contribute to a more sustainable future. So thank you, everyone. I hope you enjoyed my presentation.